So today, you guys are learning about exponential models. The goal is that you'll be able to graph exponential functions, identify features, as well as apply properties to real-world situations. And the truth of the matter is that just you're going to complete this activity, the investigation, so then that way you can kind of see and write down things that you notice about different types of formats of exponential functions. Okay, so go ahead and complete the first couple of slides. You know about exponential functions, because an exponential function is an independent variable that is where the independent variable is an exponent. So like 2 to the x, 5 times 3 to the x plus 2, 5 to the negative x. Even the exponent could be negative, but no matter what, it's still in the exponent. That's what makes the exponential function. Okay? So I want you to complete the next several slides that basically walk you through different types of exponential functions. And I want you to write down, what do you notice about them? Okay? Write down what you notice about them. So based off of this investigation, what you can really say is, in general, for any exponential graph, this is the general setup of it. K times a to the x plus c, where a is an element of Q, which stands for, say again? Rational numbers. Rational numbers are what types of numbers? And yes, real, integers, and fractions, okay? K cannot equal 0, because if K equals 0, what would happen to that first term there?
It would also cancel out.
It would cancel out, leaving you with just a constant. And A cannot equal 1. If A was 1, right, say you have something like this, what would that even look like?
Let me see.
What's 1 to any power?
1.
So whether you plugged in 2,
straight line right across 1.
it would be a straight line. Plug in 3, plug in 4, it would be a straight line right across 1. So in general, for any graph, any exponential function, we know that our y-intercept is going to be what? K plus c. So 0k plus c. And our horizontal asymptote will always be what? And your horizontal asymptotes are always written as equations. So it doesn't matter. As long as you have an exponential function, that will always be the case. Just remember, k is the number that's attached to your base, because I don't want you guys to get that confused. So let's take a look at one last one. We have a to the negative x plus c. Now compared to the other ones, this was different. Why? It's a negative x. You have a negative in the exponent. If you look at these four graphs, okay, you have 2 to the negative x and versus 2 to the x, and then you have 3 times 2 to the negative x plus 1 versus 3 times 2 to the x plus 1. Okay? But what do you notice? What do you notice about the ones that have the negative in the exponent? What are some things that you notice? Yes? But the negative x is going to be a decline. However, if it's positive, it's going to be a rise. Is that going to apply every time?
I don't know.
Okay. Well, we'll test out a few. Anything else that you notice?
Looks like the other stuff
Looks like the other stuff still
still applies.
applies?
Yeah.
What other stuff are you referring to? K plus C is still the y-intercept. Okay, let's see. Let's use this one instead. What's K for this one?
3.
And C?
1.
When I add them, do I get 4?
Yes.
Sure do. So that still applies. So that is still my y-intercept. Does the thing about the horizontal asymptote still applies? Y equals 1? Okay, so that still applies. That's still my horizontal asymptote. But yes, there is a line for a reason. There's something different about ones that are negative. There is something different about the ones that are negative. And the last one is going to reflect over the y-axis. Every single one of these is a reflection over the y-axis. You can test it out. Do 2/3 to the negative x versus 2/3 to the positive x. And you'll see it's still a reflection over the y-axis. Questions on your properties of exponential functions. Alright, application-wise, this applies with exponentials in the sense of growth and decay. Whenever you hear about people talking about like a population is growing, a lot of times it grows exponentially. Very rare does it grow linearly. Okay, like back in the 70s and 80s, the baby boomer age, the people were having babies exponentially. That's how they describe it. All right. When you look at bacteria, it grows as well exponentially. It doesn't grow linearly. Stuff like either triples or quadruples all the time. Okay. When a disease hits like a poor country or something like that, people aren't dying one by one. They're dying like in different numbers. They're usually increasing numbers. So that's another example of exponential, but not growth, decay, because people are unfortunately passing away. They're dying. The population is decreasing. Okay? So growth means things are going up versus decay, which means things are going down. Okay? So let's look at some more positive examples of real world applications. Length. That's an L centimeters, of a pumpkin plant increases according to the equation L equals 4 times 1.2 to the T, where T is the time in days. Okay? Is everyone all right? Our independent variable is our time, is our days. Okay? So depending on the number of days, the pumpkin is this going to grow or is it going to decay? Why is it going to grow? Pumpkin plants can decay, especially when they're left out too long.
It's increasing according to the equation.
And how do you know? What part of the equation tells you whether or not it's going to go up or it's going to go down?
Positive T.
Okay, I heard like a little bit of everything.
Positive T.
Not the T.
Oh, positive 4.
Your A. That 1.2. A is greater than what? Remember, 3 to the x, 4 to the x, 5 to the x, and every single one of those go up? So because it's greater than 1, it is going to represent growth. Okay? What I want you guys to do is I want you to take this equation, and I want you to find its length at different days. Okay? You got the initial day, day 2, day 4, day 6, day 8. I want you to complete this table, just like how we did the water lily example from the other day. And then I want you to graph it. I want you to graph your data, just like how we did the water lily example the other day. So you complete the table. When T is 0, what's your length? It was 4, okay? So it was just 4 times 1.2 to the 0 power. What about 6? What'd you get for 6? 11.9. 3 significant figures. What was 16?
74.0.
Okay, so when you grab, I know you filled in the rest, but just for sake of time, they had 11.6, which is actually really low, and then 74 would have been somewhere up here. This is how I labeled my triangle, and then you want to make sure you draw a smooth curve. And here it is. Yes, it goes up. This represents exponential growth. Now you can use your graph to answer follow-up questions, okay? Applications are pretty straightforward. They really are, all right? For example, how long is the pumpkin when T equals 0? How long? 4 centimeters. You found that out in your table. If you forgot, you can always plug 0 in. And it says, how long will the pumpkin be after 3 weeks? Be careful here. Your time is measured in what? Days. So 3 weeks is equal to how many days? So in this case, to figure out this example, or this answer, you actually have to plug in not 3, but 21. Do that real quick. What's 4 times 1.2 to the 21st power? 184 centimeters. And that's it. There's an application problem for you. Questions on that? future midterm coming up. It says Hubert invests 3,000 euros in a bank at a rate of 5% per annum compounded yearly. Sound familiar? What topic was that dealt with these types of problems? Interest and all that good stuff. Did you ever have to memorize that formula?
No. Compound one, yes. The other one, no.
We had two compound ones.
Oh, never mind.
And one of them you did have to remember. Who has their reference book? Pull out your reference book.
I have it right here. Compound interest is FB equals PB times parentheses 1 plus R over 100K parentheses carry K.
This was the formula. This was compound interest. This was your the one that dealt with things being compounded at different rates. Okay, what did FV stand for? Future value, which we don't know here, but we do know our present value. What's our present value? 3,000. That's how much we started with. 1 plus, what was R?
R is.
It was your rate. What's our rate here?
5%.
5%. What did K stand for?
Your
Number of compounding periods per year. So for this example, what number would it be? It's yearly, so 1. If it said monthly, it would have been
12.
And if it was quarterly, it would have been 4. And then semi-annually would have been
Wait, what semi-annually mean?
half. Halfway through the year, so twice.
So if it's
2. Think like a semicircle is half the circle. So semi-annually would be half the year.
6 months.
Yeah, even though it's 6 months, it's alwaed still in respect to a year. So half the year would be, 6 months would be 1 half the year, the other half which makes 2. And N stood for what? What did N stand for? The number of years, which we don't know. We know that let Y be the amount he had in the bank after X years. So this is X. My future value is Y. What's 5 over 100? As a decimal. 0.05. There's my function. 3,000. Sorry. There's our function using an older concept applying to a new one. Every single one that we dealt with compound interest or even continuous compounding, they all were exponential functions that we were actually writing. Every single one. So now it says to draw a graph to represent how much Hubert has in the bank after X years. Use a scale of 0 to 10 years on your x-axis, and then 2,500 to 5,000 euros on your y-axis. So, how do we do this?
Put 1 through 10 on there.
You just gotta put 1 through 10. Yeah, I think I'm gonna go by 2s here, just because of what I have. But how do I know what my y's are? What do I have to do? And what am I putting in for x?
1, 2, or 2, 4, 6, 8, 10.
I need one more. I do need 0. Because even though I kind of already know what I start with, you still need that 1 for 0. So let's plug in some values. You could do, honestly, the 0 through 10, you could actually go by 1s. But let's figure out what all these numbers are, and then let's graph it. And then I also want you guys to answer the other 2 questions that are on the next slide. So, complete that quote-unquote table, graph, and then answer the next 2 questions. It's 0. Where were you? How much?
3,000.
3,000. Now, my question to you is, let's see, I'm going to label this like this. I know you didn't get all whole numbers when you did this, so how did you round?
360. 2 decimal places.
Lee, why 2 decimal places? It's currency. Should be 2 decimal places. So, Lee, can you tell me what you got for a 6? Year 6?
4,020. 129.
4,020, and then what? 0.29. Okay. So year 6, 4,009. Okay, cool. I was here for this one. And then what about 10? So I'll stop things right here. Okay? Yes, it kind of does look a little linear, but it is indeed doing kind of an exponential type thing. Okay? So answering those last couple of questions, I think one was how much does he have after 4 years? You gotta plug in 4 for n. How much? 0.50? 5. 2.
Yeah.
I didn't even show up.
So is it still the dollar sign?
Oh.
No?
You would actually write out euros.
But what if you only
Can you
put
use the euro
5?
sign?
Is that still wrong?
It would actually be USD if it's American dollars.
So we can't reuse the money sign again?
So it would have been 52.
Oh wait, no. Oh.
Okay. Now what about this one? Says how many years is it before Hubert has 4,000 euros in the bank? This time we're looking for n. How do we do that?
Say 4,000. Plug in for Y.
What do you mean? Plug what in for y?
Plug 4,000 for Y. That was just it.
I need to do a little bit more. If I did plug this in for y.
And then we divide the 3,000 times 1.05
Mm-hmm.
to the other side, to that side, so to cancel out. Then you have to and get in.
Well, the thing is, this n is attached to that 1.05, so we wouldn't be able to
So you
divide.
divide by 3,000.
You can divide by 3,000, and yes, logs are involved if you do this algebraically, but y'all are not responsible for logs, because I would have taught that back when we did this in currency conversions. So how else can you figure out where two equations equal each other? Y1 and Y2,
Or that.
and then see what?
Where they intersect.
See where they intersect. You could also, you guys remember, did you kind of do a table to see what the values were?
Yeah.
So at 6 years, you were already over 4,000, weren't we? At 4 years, we just answered that. We were actually, weren't we under? Yeah, we were under. So what about at 5 years? We're still under?
Yeah.
So then we already know, just by using our table, that it was 6 years.
Well, it said before Herbert has, so I thought it would be 5. Herbert uses it before he has it. So I did 6 at first, and I was like, wait, no.
Well, it still would be 6. I know that word is kind of a little off, but it's actually saying, how many years is it? How many years has elapsed before he actually accumulates 4,000 euros? So let's say dollars. Yeah, that's what it's actually saying. Okay. Now, looking at the table option isn't always going to work because sometimes it won't be a whole number. Okay. So using that feature of plugging it into the calculator and seeing where the two curves intersect each other is going to be your best bet. And what it's going to look like is it's going to be an exponential function and a horizontal line, and that's what you're looking for. That particular x value. Okay? Questions on the applications of exponential